Hello, this is the Chapter 19 homework for Physics 104A. Let's start with problem number 13. It says a reversible Carnot engine operating between helium's melting point and its 4.25 Kelvin boiling point has an efficiency of 77.7%. What is the melting point? All right, so we use the equation for Carnot engine, the efficiency. Right here, efficiency is 1 minus cold temperature divided by hot temperature. And we see the hot temperature, the melting point of helium is 4.25 Kelvin. I'm sorry, the boiling point of helium. Number 27, about the ocean thermal energy conversion, OTEC, is an energy producing scheme that used the temperature difference between warm ocean surface waters in the tropics and cooler water several hundred meters down below. And it gives the two different temperatures. Here I've converted them to Kelvin. And we're to compute the Carnot efficiency, so we'll use the equation 1 minus T sub C over T sub H, and we get a pretty low efficiency of 6.7%. But then we see at the end of the problem, it says your answer may seem low, but remember that OTEC's fuel is free, meaning it's just pulling from the temperature difference between the surface water and the water that's deep under the surface. For number 36, a power plant extracts energy from steam 280 degrees Celsius. So right there I'll say T sub H is, and I'll convert that to Kelvin, 553. It delivers 880 megawatts of electric power. Now this is actually the work that's done by the engine, and in ways that we'll discuss later on in the semester, that work gets converted to electric power. So work is 880 megawatts. Now really that's a rate of work being done. It's 880 megajoules per second. But we can think of it as megajoules, an amount of work, if we just think that is how much is done in each second. And really what we're getting at is this equation that I've written on the right in the light blue, the time derivative equations. It's the rate of Q sub H plus the rate of Q sub C, equals the rate of Q sub C plus the rate of work. And those are measured in watts. That's the power equation. But often it's simpler just to think of, when it gives us watts, just to think of that as joules, recognizing that's in 1 second. And it says efficiency is 0.29. Part A, we're going to find the Carnot efficiency, 0.452. Now that is the maximum possible efficiency. Our engine that we're looking at actually only has an efficiency of 0.29, so it'll never be higher than 0.452. It'll never be higher than the Carnot efficiency, which means that it's about 2/3 of the maximum possible efficiency that it could be. Question B says find the rate of waste heat discharged to the river. So we want to find Q sub C. Efficiency is work over Q sub H. We want to get Q sub C involved in that equation, so let's substitute Q sub H as W plus Q sub C. Now I'm going to solve this equation for Q sub C, and the first thing I do is multiply both sides of the equation by W plus Q sub C, and divide both sides of the equation by E. And you can follow along and see little by little I've solved it for Q sub C, and you should get work equals 1 over E minus E. We plug in the values and we get 2154 megawatts. And again, that is 2154 megajoules per second. And then question C gives some practical use of this waste heat. It says how many houses, each requiring 23 kilowatts of heating power, could be heated with the waste heat from this plant? Well, 2154 megawatts, I want to put that in kilowatts, is 2154 times 10 to the third kilowatts. And then we're going to multiply by one house per 23 kilowatts, and we get 94,000 houses could be heated by the waste heat. Number 39, an industrial freezer maintains an interior at 17 degrees Celsius and discharges heat to the surrounding environment at 36 degrees Celsius. It consumes electrical energy at the rate of 27.3 kilowatts. Now, really what that means for our purposes is that is the work done by the motor, 27.3 kilowatts. It says find the freezer's coefficient of performance, assuming it's reversible. All right, that's just another way of saying the ideal coefficient of performance, the best possible COP that this refrigerator can get. And so we will convert our temperatures, both the cold and the hot, to Kelvin. The work is 27.3 kilojoules per second. We'll get to that later. The coefficient of performance for a reversible refrigerator is TC over TH minus TC, 4.83. Now, question B asks how much water initially at 0 degrees Celsius can the unit turn to ice at 0 degrees Celsius in 1 hour? So we want to learn something about how much heat it can extract from the cold temperature from the inside. We want to know that because if you look down the left-hand side of the page, it says we're going to use this equation for the phase change. Q sub C equals m times the heat of fusion. And so the mass, which is what we're asked to solve, is the heat extracted divided by the heat of fusion. We don't yet know what the heat extracted is, Q sub C. So let's come up here to the middle of the page. We know that coefficient of performance is Q sub C over W. So Q sub C is W times COP. And when you take the work, which is 27.3 kilojoules per second, times the coefficient of performance of 4.83, you get 131.86 kilojoules per second. That is the rate of, that's the power. The question asks how much heat can be extracted in 1 hour. So we'll multiply by 3,600 seconds. And we get Q sub C is 474,711 kilojoules. That's how much heat's going to get extracted from this water in 1 hour. Let's take this value and we'll plug it into our phase change equation for Q sub C. Notice that the Q sub C is in kilojoules. So for the heat of fusion, we're going to use the number 334 kilojoules per kilogram. And we get 1420 kilograms. Number 54, an entropy question. We have equal masses of water, 250 grams. One is hot at 80 degrees Celsius, the other is cool at 10 degrees Celsius. Find the entropy change for the hot, the cool, and the entire system. All right, so immediately I convert those temperatures to Kelvin, 353 and 283. Along the way, we're going to need to know the equilibrium temperature. So I've done that here in green. Very easy to do because they are equal masses of the same substance. So it's just going to be the average of the temperatures. So the average of 10 degrees Celsius and 80 degrees Celsius is 45 degrees Celsius. But let's get that in Kelvin, 318 Kelvin. That's the equilibrium temperature. With that in mind, let's start calculating the change in entropy. Integral of dq over t. We'll first deal with the hot water, which I've called delta S1. So water 1 is the integral of dq over t. I went through this in the lecture video, so I'll go through it a bit more quickly here, but you can refer back to my explanations in the lecture video. But q is mc delta t, so as an integral, dq becomes mc dt. And we're integrating from the original temperature, which is T1, to the equilibrium temperature, T. The MC gets factored out to the left. We're left with taking the integral of dt over t, which becomes the natural logarithm. So we're left with MC natural log of t over T1. When you plug in t and T1 and m and c, let's go to the bottom of the page. I only remembered to do this as an afterthought to answer the question. The change in entropy of the hot water is negative 109.22 joules per Kelvin. Let's do the same for the cool water, delta S2. And so we take the integral. It's exactly these same steps. Only difference is the lower limit of integration is T sub 2, the initial temperature of the cold water. So we get MC natural log of T over T2. And let's go to the very bottom of the screen. When you plug in those values, you should get 121.97 joules per Kelvin. And so now you just add those up. The next two lines that I've written in hand just show me, I just show adding them all together. Here I've got M and C factored out. But in the end, you get the final answer of, when you add them together, 12.7 joules per Kelvin. And as expected, the total entropy, when you take for the cold water plus the hot water, it increases. Number 57 says, find the entropy change when 2.4 kilogram aluminum pan at 155 degrees Celsius is plunged into 3.5 kilograms of water at 15 degrees Celsius. All right, so it's a bit more complicated, just a bit more than the previous problem, number 54, because we first have to find the equilibrium temperature. It's not so easy as when you had equal masses of the same substance. So we need to remember back to previous lessons how you find the equilibrium temperature. We've got aluminum, and I'll say M sub A for aluminum, M sub W for water. We have their temperatures, and we have the specific heat of aluminum 900, specific heat of water 4184. So on this page, I'm going to calculate the equilibrium temperature. QA plus QW equals 0. And then we're going to separate that into MACA times the change in temperature for the aluminum plus M water, C water times the change in temperature for the water equals 0. And over the next few lines, I go through the algebra of solving for T. And we did this back in chapter 16. In fact, if you want a quick review, example 16.2, finding the equilibrium temperature that involves an aluminum frying pan plunged into cold water. So it takes you through it. But in the end, we've got the formula that's at the bottom of the page. The equilibrium temperature is, and make sure you can go through all this and do this work. But it comes out to be 33.00 degrees Celsius, 306.15 Kelvin. Okay, that's the equilibrium temperature. And now we can start solving for entropy change. So there it is again, the equilibrium temperature. For the water, we have delta SW is integral of dq over t, which is the integral of mc dt. Once again, same as we've done before, mc gets factored out to the left. It's the integral of dt over t, and the limits of integration are the original temperature of the water to the equilibrium temperature. So mc times natural log of t over tw equals, and there it is. I've plugged in the values, and we get plus 887.3 joules per Kelvin. For the aluminum, the change in entropy of the aluminum is mc natural logarithm of t over ta. Plug those in, we get negative 724.5 joules per Kelvin. And so when we add those together, the change in entropy of the water plus the change in entropy of the aluminum, we get plus 163 joules per Kelvin. And I'll just round that to 160 joules per Kelvin. Now, with number 57, it's also possible to do it the non-calculus way, using an estimate. So remember in the lecture, I said that you can use non-calculus estimate, assuming that temperature doesn't change that much. And I didn't really specify what it means for temperature to not change that much, but it's useful to try it with this problem and see how far off we get from the calculus version answer. So I recommend that you also do this problem with the non-calculus estimate. And we'll just see in this particular problem how far off we get from the true answer. So on this page, I'm going to do the non-calculus estimation where change in entropy is, instead of doing the integral, it's just Q over the average temperature. All right, so for the water, Q over the average temperature. Now, average temperature is going to be 1/2 of the equilibrium temperature plus the original temperature. And Q is MWCW times delta TW. So I'll plug all those in, where delta TW is the 33 degrees Celsius minus 15 degrees Celsius. And there I've got the equilibrium temperature and the initial temperature, and those have to be in Kelvin for this to work. And we get a change in entropy for the water of 887.1 joules per Kelvin. Now, on the previous problem, you can look back and see it was 887.3 joules per Kelvin. We do the same for aluminum, MaCa delta Ta, that's the Q in the numerator, over the average temperature that the aluminum goes through, and that's the equilibrium temperature plus the original temperature of the aluminum, and we get negative 717.7 joules per Kelvin. And originally, when we did it the calculus way, we got negative 724.5 joules per Kelvin. Now you notice the differences. Here we've gotten for the water, it really wasn't that far off from the calculus solution, and that's because the water's temperature didn't change much. And so the estimate is pretty good. The aluminum's temperature changed significantly, and so we get more of an error. We get about a 1% error. Well, in the end, we can add them up, the entropy of the water plus the entropy of the aluminum, and we get plus 169.4 joules per Kelvin. I'll round that for two significant figures to 170 joules per Kelvin. And keep in mind the original answer on the previous page when we did calculus was plus 160 joules per Kelvin. So our answer is kind of close. And we end this chapter with three pretty quick, straightforward passage problems. The passage says, refrigerators remain among the greatest consumers of electrical energy in most homes. In the course of a day, one kitchen refrigerator removes 30 megajoules of energy from its contents, in the process consuming 10 megajoules of electrical power. The electricity comes from a 40% efficient coal-fired power plant. All right. So number 75 says the refrigerator's COP is what? And for that, we're just going to use Q sub C over W. Remember, coefficient of performance is what you want, which is heat extracted from the cold area, divided by what you must provide, and that's work done by the motor. So 30 megajoules over 10 megajoules, and we're left with 3. Question 76 asks, it says the fuel energy consumed at the power plant to run this refrigerator for the day is what? And so power plant, we have efficiency is the work done divided by the fuel. And so the fuel that it's asking about is going to be the work divided by efficiency. Now, the work, even though at the power plant it's not work, it's electrical energy provided, but it's the W that applies to our refrigerator. It's the work that our motor does. So we're still calling it W. W over E, 10 megajoules over, and it said in the passage it's a 40% efficient coal-fired power plant. So 10 megajoules divided by 0.40 means that the energy consumed at the power plant is 25 megajoules. Question 77. The total energy rejected to the surrounding kitchen during the course of the day is what? Well, that's Q sub H, and it's Q sub C plus W, so 30 megajoules extracted from the inside of the refrigerator, plus the 10 megajoules of work that the motor does, and we get 40 megajoules that are rejected into the surrounding kitchen. And that's all for the Chapter 19 homework. Have a great day.